In this video, we're going to take a look at acid-base titration curves. An acid-base titration curve is just a plot of the pH of the solution being analyzed versus the volume of titrant added. We're going to be analyzing three different titration curves: strong acid, strong base titration curves, weak acid, strong base titration curves, and strong acid, weak base titration curves. Each scenario will have its own distinct titration curve with its characteristic shape and features, and a different equivalence point that's going to require us to use an appropriate indicator whose pKa is matching the equivalence point, or at least should be close to the equivalence point. Notice that there's no weak acid, weak base titration since the reaction must go to completion. One of the acids or bases must be strong to drive the reaction to completion. First, we're going to take a look at strong acid, strong base titrations. We're going to analyze four distinct parts of the titration curve: the initial pH before any titrant is added, the pH at halfway to the equivalence point, the equivalence point, and the pH beyond the equivalence point. In this situation, the sodium hydroxide is being added from the burette, so it is the titrant, and the HCl, hydrochloric acid, is in the Erlenmeyer flask, so it is called our analyte. We're going to start by writing the formula and net ionic equations for the reaction as shown here. Notice that the sodium ions and the chloride ions are spectators in this situation. First, we're going to describe the strong acid, strong base titration curve from a qualitative perspective. Since the acid is strong, the initial hydronium ion concentration is high and the pH will start out low. This will continue to be the case as long as the strong acid remains in excess over the base. The pH will slowly rise as the moles of sodium hydroxide is added and almost equals the moles of hydronium ion. When the titration is within a drop or two of the equivalence point, we see a drastic rise in the pH. The equivalence point is reached when the moles of hydroxide ions from the base is equal to the moles of hydrogen ions from the acid. If we were to continually to add sodium hydroxide beyond this point, the pH would continue to drastically rise as the hydroxide ion concentration now exceeds the hydronium ion concentration. And we wouldn't want to do this, of course, in a real titration. This would be called overshooting our endpoint. The pH would then start to level off as the hydroxide ion concentration approaches 0.10 molar. To calculate the pH, the initial pH prior to the addition of any titrant, we need to recognize that hydrochloric acid is a strong acid and therefore its concentration is equal to the hydronium ion concentration, which is 0.100 molar. So to get the pH, we're just going to take the negative log of 0.100 molar, which is 1.000. In this problem, we're going to calculate the pH halfway to the equivalence point. So this is when 12.50 mils of sodium hydroxide has been added to the 25.00 mils of hydrochloric acid. So I'm going to first find out my initial concentration of hydrochloric acid, and I need to remember here that there's a dilution effect as I've now added sodium hydroxide to my analyte. So I'm going to take 0.100 molar and multiply it by 25 mils over the total volume now of 37.5 mils. That gives me an initial concentration of hydrochloric acid of 0.0667 molar. I'm going to go ahead and do the same thing for sodium hydroxide. Once I have my initial concentrations of my acid and base, I'm going to set up an ice table. And from this problem, we can see that the hydrochloric acid is still in excess over the sodium hydroxide. And so the sodium hydroxide is going to neutralize the acid, but I'm still going to have 0.0334 molar hydrochloric acid in excess. I'll have no sodium hydroxide, as it's been completely neutralized by the excess acid. And I have 0.0333 molar sodium chloride, but sodium chloride is a neutral salt and doesn't hydrolyze and therefore won't affect the pH of the solution. So to get the pH of the solution now, I'm just going to take the negative log of the hydrochloric acid concentration, which is the same as the hydronium ion concentration since it's a strong acid. And that turns out to be 1.477. In this problem, we're going to calculate the pH at the equivalence point. So we've now added 25.00 mils of 0.1 molar sodium hydroxide to our 25.00 mil of 0.1 molar hydrochloric acid. We're going to start the problem the exact same way, calculating the initial concentration of hydrochloric acid and sodium hydroxide, taking into account the dilution effect. Next, I'm going to set up an ice table. Again, I can ignore water. And we can see here that the initial concentrations of my acid and base are equal to each other, and therefore they're going to completely neutralize each other. I'm going to be left with no moles of hydrochloric acid, and I'll have 0 moles of sodium hydroxide. I will produce 0.0500 molar sodium chloride, but again, it is a neutral salt, therefore it won't hydrolyze and affect the pH of the final solution. Reminder, we can't have an aqueous solution with 0 concentration of hydronium ions since water autoionizes. So by taking the square root of the Kw, we can get the hydronium ion concentration, which is 1.00 times 10 to the negative 7, and therefore the pH should be 7.000. That's 3 decimal places, since the concentration had 3 sig figs. So whenever we have a titration involving a strong monoprotic acid and a strong base, the equivalence point is going to be at a pH of 7, since neither of the ions present in the product salt can undergo hydrolysis to affect the pH. I'm going to let you go ahead and try this next question on your own, calculating the pH beyond the equivalence points. You should be setting up the equation the exact same as the previous questions. In this case, the hydroxide ion concentration should be in excess. And so remember, when you take the negative log of the hydroxide ion concentration, you'll get the POH, not the pH. Good luck. In the examples we just worked through, remember that sodium hydroxide was our titrant and hydrochloric acid was our analyte. We should be familiar with the reverse situation as well, where the hydrochloric acid is the titrant and the sodium hydroxide is the analyte. And so everything we talked about still applies, but the situation is in reverse.